All right, let's have a look at integrating our exponentials. So going back the other way. So if I have to integrate our exponential, well, this time I'm just looking at a linear function, and so it'll simply be 1 over the coefficient of x, because if we were to differentiate, we would multiply by the derivative, and if it's a linear function, the derivative would be a. So if we're integrating, we're going back the other way, we've got to divide by the a. But that's really limited in functions you can use that for. So it's easier if we think of it that idea, hey, can we create the derivative times some function? So we're looking for that. We're looking for derivative times e to the power of a function. And if we can't get that, we want to create that. But once we've got it, we know it must have gone back to e to the function x. So if I see e to the 5x, well, I could use the first idea for that one. It's nice and simple, linear function. 1/5 e to the 5x plus a constant. If I use the second idea, what I'd be doing is saying, well, hang on, I want the derivative times e to the function. So I want 5e to the 5x. I can't just change the question, so to balance it out, I multiply by a 5th out the front. But now that integral of 5e to the 5x must go to e to the function x, in this case, e to the 5x plus a constant. We get the same thing. So possibly with a linear function, it's easier just to go, oh well, 1 over the coefficient of x e to what have you. X e to the x squared then. I would like derivative times e to the x squared. Now the derivative of x squared is of course 2x. So I would like 2x. Let's create the 2x, but then I've got to halve it as well to balance it out. I now have derivative e to the function, so I know that will go to e to the function. So I get half e to the x squared. The third one, well, it's a linear function, so I know I could just go 1/9, or using the second idea, I said, well, the derivative would be 9, so I would like 9e to the 9x minus 5, but to balance it out, I need 1/9, and so we get the 1/9 e to the 9x minus 5. The square root of e to the power of x, I've got to put it into index form first of all. So that's e to the half x, or x on 2, however you prefer to write it. That is a linear function, but I'll do it the second way. So the derivative of x on 2 would be a half. So I would like a half e to the x on 2, balance it out. I need 2 out the front, so I end up with 2e to the x on 2. I always like to answer the question in the format that they gave the question. So they put it in with square root, so I'll go back to 2 times the square root of e to the power of x. We don't have a product rule, of course, for integration like we do for differentiation. So we'll need to expand that out first, and then we can just integrate each individual bit. And they're all linear functions there, so I could just go 1 over in the first one, 1 over 2. Well, e to the x is just going to be e to the x, and 3 becomes 3x. Okay, we don't have a quotient rule, but in this case we can simplify that fraction down. And both are linear functions. Be careful with this one though, because of the negative x. So we would end up with, yes, we'll get a third e to the 3x for the first one, but it'll be plus e to the minus x, because the derivative of negative x is negative 1. Right, let's do a definite one. E to the x cubed. Well, derivative of x cubed is 3x squared, so I would like 3x squared. So to balance it out, 1/3. 1/3 e to the x cubed, sub in 1, sub in 0. Well, e to the power of 1 is e. E to the power of 0 is, of course, 1. Well, what about if the base is not e? We saw that when we were differentiating it, we did it exactly the same, but we multiplied by the natural log of the base. So logic says if I'm going back the other way, if I have to integrate one where the base is not e, I'll do it exactly the same, but I'll divide by the natural log of the base. So that one will be 3 to the power of x over log 3. Okay.